Okay, so far we have learned how to convert a physical model into differential equation, right? From a physical model into a differential equation, right? And then we also learn how to convert the physical model to transfer function, right? In fact, we convert them from differential equation to the transfer function as well as from the physical model itself. So now there's the other representations we have learned before is to convert from physical model into a state space model, right? So we have state space model. All right, there are at least three type of representations here. So the first one, differential equation, transfer function, and state space. All right. So as you can see from the slides on the left, so we have physical models. Can be a mechanical systems, electrical systems, mechatronic systems. Then we can convert them using the theorems, math theorems, Newton laws, Ohm's laws, Kirchhoff law, and whatnot. Then we can convert them into mathematical models using differential equations, state space, and transfer function, right? But now we want to see how we could convert them between this model. That means from differential equation to state space, we already learned before. State space to transfer function, and transfer function to differential equation. All right. Let's see how to convert transfer function to state space model. We know that state space model has two equations, which is at x dot equal to ax plus bu, and y. The output equation is y equal to cx plus du. All right. In fact, this A, B, C, and D represents by this block diagrams, where A is the system matrix, C is the output matrix, B is input matrix, D is feed forward matrix. Okay. So we straight to the example. I'll show you a simple one. You can try the rest. Okay, let's do because the transfer function can be in this form or in this form, right? So for the first one, transfer function with constant term in numerator. In numerator, there's a constant term here. The second one is the polynomial equations in the numerator. All right, s plus 3 here. So we have to treat slightly different. All right. Now let's do this example A, which is C of S or R of S 1 S squared plus 6S plus 14, right? So we could change this, we could convert this into a differential equation, simply cross multiply C of S, so which is S squared plus 6S plus 14, C of S equals to R of S. All right. So to differential equation, we can simply, let's say we could rename C of S to be X, or you can use CT as well. So D C ct over dt squared plus 6 dc of t over dt plus 14 c of t equal to CRT. Right? Okay, I think we did it before in my previous lecture. We know that if we, because we need to find how many states before we convert to state space, we need to see that the order of the system is second order systems. We're going to have 2 states, right? So important is how many states that the state space has. How many states? Vector. So in this case, second order system, we have 2 states vector, right? 2 state vectors. And then how many states? 2 states. All right. What is the output? Because in this case, the output is CS, that means CT, right? So the output is Y equal to C of T, right? So this is the parameter that we need to know. All right, then we can rewrite again. Let C of T equal to x1. All right. So we will have d square x1 over dt squared plus 6 dx1 over dt plus 14 x1 equal to maybe RT equal to UT, right? That's R of T equal to U of T. Okay, so that should be UT. Then we know that this is x1, this is this is x1, this is x1 dot, right? This is x1 double dot. These terms here, right? All right. Now we know that we found that there's one derivative of the state vector. This one is double derivative, so we need to find another first derivative. So let x1 equal to x2, and then x1 dot equal to x2 dot. All right. So then we have these 2 derivative of the state vector. We have 2 state vectors. That means earlier we found that in this transfer function we need to find 2 states vector. All right. Then we can write these equations because we know that x1 dot equal to x2, because in state space we have to write x dot equal to ax plus bu and y equal to cx plus du. All right. Okay. Now we have x1 dot, x2 dot. Then we can write this x1 dot x1 dot equal to x2. That is our first state equation, right? So x2 we have to rearrange that x2 dot here, x2 dot plus 6 x2, because we need to use a state, not derivative, so we use x2 plus 14x1, again there is states, and then u of t. Then we need to find what is x2. This is minus 14x1 minus 6x2 plus u of t. Okay, that is our second state vector. No, second state equation. Then we can use this. You can use this equation to write our state equation, which is x1 dot x2 dot equal to, so we need to write this matrix first, plus b u t. So this is a, this is b, this is ax. So states, how many states we have? So we have two states, x1, x2. Matrix A have to be 2 by 2 because second order. If it is third order, then 3 by 3. So in this case, x1. So x1 is equal to x2, which is 0, 1. It's x2, and then 0. x2 equal to minus 14x1. Yeah. Minus 6x2 plus ut1. Okay, that's what we have right now. And then this is our state equations. Our output equation y equal to, we define that y equal to x1 because x1 is the output. So in terms of matrix, we need to write the same way, x1 and x2 state vector. Then y equal to x1, which is 0, 1. So there's no d, there's no feed forward, right? Because this d is here, so we don't have that. All right, that is our state space that we convert from transfer function to state space. All right, now we need to use the same okay, probably I need to show you this number 2 first. So we've done example number 1, so you can try example B here. So I'm gonna try this, I'm gonna solve this transfer function with polynomial in the numerator. So first we have to do the same thing. So in this case we have to separate that numerator and denominator. So we have the inputs here, r of s, is 1 over s squared plus 9 s plus 10. Then we have another block diagrams here just to represent the numerator, which is s plus 3. And then this is the output of C of S. Okay. This is the example for 2A. Right? Example 2A, we have that. Okay, we have to do the same and this one as before, which is this is this will represent the state equation. This one will represent the output equation. Assume that This is our x1, which is earlier, this is our output, right, y. But now the output is here. So this is our temporary outputs. This is our output is here, right? Okay. So that means if we convert this to state space, we're going to have x1 dot, x2 dot equals to 0, 1. Okay, and then we're going to have minus 10, minus 9, x1, x2, plus the same thing, bu, which is a 0, 1, ut. That is our input equation. There's no change, just follow this, the previous example, you get this. Okay, as for the outputs, we have this because the y, all right, so we need to multiply x1 with this numerator here, which is we get this x1 s plus 3 equals to s x1 plus 3x1. All right, so this is a derivative terms. So that means this is x1 dot, right? So we have to, because this is x1 at s, so we can simply change that to x1 dot, right? So this x1 dot and x1. Okay, x1 dots, we know that it is, because we are not going to produce the state equation in terms of derivative of the state vector. We need to convert that into purely the vector. Convert that to vector. So this is derivative. We don't want this. We need to convert to x2 because x2 is equal to x1 dot, right? So that means our this equation will be x2 plus 3x1. So that will be equal to y, right? That will be equal to y. So that means our y equal to 3x1 plus x2. So then we can simply write in terms of metric form, where this is our matrix, this is x1 and then x2, there's 3 and 1, right? So this is our output equations. Output equation. Okay, this is our state equation. All right. State equations here. This output equations here. Okay. You can do the same for this, for the example in B, for both cases, right? So now we want to see how we can convert the state space into transfer function. Okay. Okay, let's have a look at this state space that we actually derived from example 1a here. We got this. Now we need to convert them into transfer function. Alright. So how to convert the state space to transfer functions? So basically the state space and output equation are this one. And then we convert to Laplace domain, which is Laplace this one and Laplace this one. We get this Sx of s equal to Axs plus Bus. Then convert this to Laplace, we got this. And then we then substitute xs into ys, we got this. Alright, this is the formula to convert this state space here two transfer functions, then we can simplify that y of s equal to c si minus a b inverse b plus d. Alright, how to do that? We can solve the example one, which is derived from the previous transfer functions to state space. Now we're going to change back to transfer function. Alright. Okay. Now, okay, y of s equal to c s identity matrix minus a inverse matrix b plus d. So we need to find this term first. Alright, si minus a. Si minus a equals to, so s is because this is 2 by 2, right? 2 by 2, we have to multiply s. We have to multiply s with identity matrix, which is 1 0 0 1, s minus a. 0 1 minus 14 minus 6, so which is s 0 0 s minus 0 1 minus 14 minus 6, which is s minus 0 s 0 minus 1, which is minus 14 s minus 6 s plus 6. Right. Okay. Now we solve this si minus a. Okay. Now we need to find the inverse, because the complete equations ask for si minus a inverse, right? So we need to find si minus a, which is adjoint, metric adjoint of si minus a over determinant, right? Determinant of si minus a, right? So determinant, we can find the s plus 6 minus plus 14. Okay, so that means s squared plus 6s plus 14. So the adjoint is change place, then negative of these two, right? So which is basically s plus 6 minus 14, 1, and s. Still number matrix. Alright, so this is the solution for si minus a, this one. Alright, then we need to use this to substitute this in the main equation here, which is we have to multiply by c. Okay, so we have that. Then y of s equal to c. What is our matrix c? So you can refer here, c is 1 0. This is a, b, and c. Okay, c is c s I minus a inverse b plus d, right? So we don't have d in this case. So c is 1 by 2, 1 0, 2 by 1 0. This is s plus 6 minus 14, 1s, and then this not b is 0 1. This is our b here, right? So solving this, we have s plus 6, s plus 6, 0 plus 1. Alright, plus 6, 0, 1, 0, okay, 1. And then we have a 0, 1 here. That is 0 plus 1, so we have 1. So don't forget our determinant just now. This is just to solve the top parts here, right? So our determinant is still there, squared plus 6s plus 14. So that will actually represents our transfer function ys over c of s. Alright. So if we compare this, you should be getting back the original transfer functions here, s squared plus 6s plus 14. We convert that into here, and then we find back this one. All right. I think we have covered all the three representations from differential equations, transfer functions, and state space equation. Okay, I think that's all for this topic. Then we will probably move on to the analysis part. Thank you.